Hello, my dear friends, and welcome back to Hafi Sleep. Whether you're here to unwind after a long day, to drift off into a peaceful rest, or simply to explore the cosmos from the comfort of your bed, I'm so glad you found your way here. Tonight, we're embarking on a truly cosmic journey, one that will gently stretch your mind before we let it relax completely. We're going to explore a question that has puzzled the greatest thinkers for centuries. Is time just an illusion? We'll wander through the flexible clock of our own minds into the absolute time of Newton and then dive into the mind-bending relative time of Einstein. We'll see how gravity warps the fabric of space-time itself and how the entire universe might be moving from order to chaos, giving us our arrow of time. It's a story of physics, philosophy, and profound wonder, all told in a way that's easy and soothing to follow. As we begin this journey together, I have a small request. If the sound of my voice helps you relax, if these ideas spark your curiosity, please consider supporting our little community here. Subscribe to the channel and give this video a like. It truly helps us grow and bring more calming content to you. And I'd love to feel connected to all of you wherever you are in the world. As you get cozy, please take a second to comment down below and tell me your location and what time it is for you right now. Are you watching from a bustling city at midnight? A quiet countryside at dawn? Let's create a beautiful global map of everyone who is relaxing and exploring with us tonight. Now find your most comfortable position, let your breathing become slow and deep, and let your thoughts begin to soften. Let's leave the clocks behind for a while and ask together, what is time really? Have you ever had one of those afternoons that just drags? Maybe you're in a class that feels like it will never end, or you're waiting for a text back from someone, and you find yourself staring at the clock, watching the second hand crawl its way around the face with a kind of lazy, agonizing slowness. Each tick feels like a minute. Each talk feels like an hour. Time in that moment becomes a thick, sticky substance you have to wade through. Now, flip the script. Think about a vacation, or a weekend spent with your best friends, or that feeling when you're so absorbed in a project you love that you completely forget about the world. You look up at the clock and, what? 3 hours have vanished in what felt like 3 minutes. It's like a thief in the night, a magician who's stolen a chunk of your life without you even noticing. So, which one is real? Is time the slow, grueling crawl of the boring class? Or is it the fleeting, slippery phantom of the good times? How can the same thing, this thing we call time, feel so utterly fundamentally different depending on what we're doing? It's a mystery we all live with every single day. We are ruled by it. We wake up to its alarm. We race against it to meet deadlines. We mourn its passage as we grow older. We measure our lives by its relentless march. Seconds, minutes, hours, days, years, centuries. It's the invisible fabric our lives are woven into. But what if I told you that this fabric, this relentless tyrant we all serve, might not be as solid as it seems? What if the clock on your wall and the calendar on your phone are telling you a story that, at the most fundamental level of the universe, is just a little bit fictional? What if time, as we experience it, is a magnificent, necessary, and utterly convincing illusion? That's the incredible mind-bending journey we're embarking on today. We're going to ask the question that has haunted philosophers for millennia and physicists for centuries. Is time just an illusion? And if it is, what in the world is actually ticking away on that clock? To unravel this, we'll need to become detectives of the cosmos. We'll look at the case files from our own brains, from the ancient thinkers who first wrestled with this concept, from the genius of Newton and the revolutionary madness of Einstein, and from the strange, shadowy world of quantum mechanics. We'll see how time is woven into the very fabric of space, how it might be connected to the disorder of the universe, and whether the future might already be out there, waiting for us, just as solid and real as the past. So find a comfortable seat. Take a deep breath. Don't worry about the clock for a while. Let's step outside of time for a moment and see if we can figure out what this mysterious force that governs our existence truly is. Our story begins not in a laboratory or a lecture hall, but inside the most complex timekeeping device we know, the human mind. Because the first and most immediate way we experience time is through our own perception. And as that boring class and that fun vacation prove, our internal clock is wildly unreliable. It's a flexible, stretchable, compressible thing, a clock made of jelly rather than gears. This subjective time, this felt time, is our brain's best guess about the flow of events. It's not a direct readout of some cosmic timer. Think of your brain not as a perfect recorder, but as a brilliant, overworked editor in a film studio, constantly taking in raw footage from your senses, sights, sounds, smells, touches, and frantically stitching them together into a coherent story, a movie of your life. This editor is so good at its job that it even smooths over the gaps. You know how sometimes a clock seems to freeze for a second when you first glance at it? That's because your brain, in its editing process, sometimes backfills a perception. It literally takes the image of the clock you see a fraction of a second after you've looked and splices it back into the beginning of the shot, making it seem like you saw that second for longer than you did. It's a glitch in the matrix of your mind. So, what makes this internal editor speed up or slow down the film? One major factor is novelty. When you're in a new situation, like the first day in a new city on vacation, your brain is on high alert. It's absorbing massive amounts of new data, new streets, new smells, new languages, new faces. Your internal editor is working overtime, processing every little detail. Later, when you look back on that memory, it feels long and rich because the film reel is so densely packed with fresh scenes. Contrast that with your daily commute, a route you've taken 1,000 times. Your brain is on autopilot. It doesn't need to record every single tree, every crack in the pavement. It compresses the experience, creating a much shorter, less detailed memory. In retrospect, that week of vacation feels longer than a routine week at work because the memory file is so much bigger. Emotion is another powerful time-warping tool. In moments of high adrenaline, a car accident, a sudden scare, time seems to slow to a crawl. This is likely an evolutionary gift. Your brain is kicking into hyperdrive, processing information at an incredible rate, looking for any possible escape route or solution. It's dumping a chemical cocktail into your system that heightens your senses and speeds up your cognitive processing. You're taking in more frames per second in that moment of crisis, so when you play the memory back, it feels like it happened in slow motion. The editor has used a slow motion effect on that particularly intense scene. Then there's attention and focus. When you're deeply engrossed in a task, a state psychologists call flow, you are fully immersed in the present moment. Your brain isn't busy jumping between thoughts of the past and future. It's not checking the clock. It's completely in the zone. Without the constant internal nagging of, what time is it? The perception of time's passage simply vanishes. You are, in a very real sense, stepping out of the stream of time as your mind usually constructs it. The editor is so focused on one beautiful, continuous shot that it forgets to add the time code at the bottom of the screen. So, even before we step out into the wider universe, we find that our most personal experience of time is a construct, a clever simulation run by our brains. It's a useful interface for navigating the world, but it's not the absolute truth. It's the dashboard clock in the car of your consciousness. Usually helpful, but sometimes it glitches, and it certainly isn't the engine itself. This idea that time might be a construct of the mind is an ancient one. Long before we had fMRI machines to peer into our brains, philosophers were pondering this puzzle. St. Augustine, writing in the 4th century, was utterly baffled by time. He famously said, "What then is time? If no one asks me, I know what it is. If I wish to explain it to him who asks, I do not know." He concluded that time was fundamentally a psychological phenomenon. The past, he argued, exists only as memory in our minds. The future exists only as expectation. The present is just a fleeting knife-edge moment that is constantly vanishing into the past. For Augustine, time wasn't out there in the world. It was in here, in the human soul. The past, present, and future were a distension of the mind. This is a profound and beautiful thought. It suggests that without a mind to remember the past and anticipate the future, the concepts of past and future have no meaning. A rock doesn't have a past or a future, it just is. It exists in a perpetual, undifferentiated now. But we, as conscious beings, stretch our awareness across this landscape. We pull the past into the present through memory, and we reach forward into the future with our plans and fears. We are time travelers in our own minds. And that idea of Augustine's, that time is a distension of the mind, is like a key trying to fit a lock we can't quite see. It feels right, doesn't it? That the past is just a collection of memories, ghost images we carry in our heads, and the future is just a sketchpad of hopes and worries. It makes time feel personal, intimate, a story written by and for each of us. And that rock, just sitting there, existing in its eternal now, it's a powerful image. It suggests that the universe, in its raw, non-conscious state, might be utterly timeless. The comings and goings of galaxies, the birth and death of stars, the slow erosion of mountains, without a witness, without a mind to record it, to mark a before and an after. Are these events truly happening in time, or are they just happening? Is the universe, at its heart, just a vast, silent, and static photograph? But then we have to ask ourselves, is our mind really that powerful? Can it conjure something as pervasive, as seemingly fundamental as time, out of nothing? It's one thing to say that our experience of time's flow is a mental construct, a beautiful and necessary illusion crafted by our brains to help us navigate the world. But is it really just a story we tell ourselves, with no basis in external reality? That feels like a step too far. After all, the world outside our heads seems to play by temporal rules. Causes always come before effects. We never see a shattered glass reassemble itself and leap back onto a table. We never see a river flow backwards up a mountain. The universe seems to have a built-in arrow, a direction, that doesn't rely on us to point the way. This is the point where our investigation has to get up from the philosopher's comfy armchair and step into the laboratory. We have to leave the world of introspection and enter the world of measurement, of mathematics, of the physical cosmos. Because if time is more than just a mind game, physics should be able to find it, to weigh it, to describe its laws. Enter Sir Isaac Newton. In the 17th century, Newton gave us a picture of the universe that was majestic, logical, and absolute. In his world, space was a vast, fixed, and immovable stage, and time was a universal, relentless river that flowed through this stage at a constant, unchanging rate, independent of everything else. It was the same for everyone, everywhere, no matter what they were doing. If you were here on Earth, or on a distant star, or floating in the emptiness between galaxies, 1 second was 1 second. This was absolute time. It was a perfect cosmic clock ticking away in the background of the universe. This idea made perfect sense. It's almost hard for us to imagine a world where it wouldn't be true, because it's so deeply woven into the fabric of our daily experience. Think about it. When you make a plan to video call a friend who lives in a different time zone, you both consult a chart and agree on a specific time. You inherently believe that the moment you both label 8 p.m. is the same moment, regardless of the miles between you. You trust that time is a universal standard. When a mission control team on Earth sends a command to a rover on Mars, they calculate the delay based on the distance the radio waves have to travel, but they never for a second doubt that a second for them is a second for the rover. Time, in our practical lives, is this reliable, unwavering constant. It's the great synchronizer of human activity, and this is precisely the world Isaac Newton described. It was a world of sublime order, a cosmic empire ruled by strict mathematical laws. And for this empire to function, it needed two things: an absolute stage to perform upon, and a perfect, unchanging conductor to keep the beat. The stage was absolute space. The conductor was absolute time. Let's picture this absolute space. Don't think of empty blackness with stars in it. Think instead of an infinite, crystal-clear, immovable block of glass. It's perfectly transparent, utterly rigid, and it goes on forever in every direction. This block doesn't do anything. It doesn't expand, it doesn't contract, it doesn't wobble. It just is. It is the container for all of creation. Every single thing in the universe, every atom, every person, every planet, every star exists at a specific, fixed location within this infinite glass block. You are here, the moon is over there, the Andromeda galaxy is way, way over there. These positions are real and absolute. If you are sitting perfectly still in your room, you are absolutely at rest relative to this fixed stage of space. It provides the ultimate reference frame for all motion. Now, into this static, frozen stage, Newton introduced absolute time. If space was the infinite glass block, time was a magical, invisible river flowing through it in one direction at one speed forever. And this river had a very special property. Its flow was completely independent of everything it flowed past. Nothing could affect it. You couldn't dam the river, you couldn't speed it up, you couldn't slow it down. It was unaffected by matter, by motion, by energy, by thought. It just flowed. 1 second was 1 second, period. It was the same for a mayfly that lives for a day as it is for a star that burns for billions of years. The tick-tock of this cosmic clock was the heartbeat of reality itself. This gave Newton a wonderfully simple and powerful framework. In this universe, the concepts of here and now had absolute meaning. An event didn't just happen. It happened at a specific point in absolute space and at a specific moment in absolute time. The universe, in a way, was a giant pre-recorded movie. The entire film, from the opening scene of the Big Bang, though Newton didn't know about that, to the final credits, already existed on the reel. The past was the part of the film that had already been projected onto the screen. The future was the part of the film still coiled up, waiting its turn. And the present? The present was that single brilliant point of light from the projector's lamp, illuminating one frame at a time, creating the illusion of movement and change. But every frame, every past, present, and future moment was already there, fixed and unchangeable. This is a concept known as determinism. Since every object in this universe obeyed Newton's strict laws of motion and gravity, if you could know the exact position and velocity of every single particle in the universe at any one moment, and if you had a big enough brain to do the math, you could use Newton's laws to calculate the entire future of the universe, and even rewind it to see its entire past. There were no surprises. The universe was a clockwork mechanism of breathtaking complexity, but a mechanism nonetheless. Every gear, every spring, every tick and every tock was predetermined from the very beginning. Free will, in this view, becomes a very tricky philosophical problem. Are we truly making choices, or are we just complex biological machines playing out a script that was written into the laws of physics at the dawn of time? Now, why was this idea so powerful and so enduring? Because it worked with spectacular precision. It was incredibly useful. Let's look at how this played out in the real world. Take the journey of a cannonball. Before Newton, aiming a cannon was a bit of a black art, based on experience and rough guesswork. But with Newton's laws, you could treat the cannonball as a simple object moving through absolute space and absolute time. You could calculate the exact force of the gunpowder explosion, the initial velocity. You could factor in the constant downward pull of gravity, and you could account for air resistance. Using calculus, a mathematical tool Newton invented for this very purpose, you could plot the cannonball's entire trajectory, its parabolic arc, from the mouth of the cannon to its eventual impact. You could know precisely where it would land and when it would get there. Space and time were the graph paper on which you could draw the line of its flight. On a grander scale, look at the planets. For millennia, the motion of the planets in the night sky was a profound mystery. They seemed to wander against the backdrop of fixed stars. The word planet comes from the Greek for wanderer. Johannes Kepler had discovered that their orbits were elliptical, but he didn't know why. Newton provided the why. His law of universal gravitation stated that every object in the universe attracts every other object with a force that depends on their masses and the distance between them. The sun, with its enormous mass, creates a giant gravity well in the fabric of absolute space. The planets, like marbles rolling around a funnel, are caught in this well. Their elliptical paths are a perfect balance between their forward momentum, trying to fly off in a straight line as per Newton's first law, and the sun's gravitational pull, constantly tugging them inward. And the key here is time. Newton's equations for gravity use absolute time as the independent variable. The t in his famous equations is the same t for the Earth, for Mars, for a comet in the Oort cloud. This universal clock is what allows the solar system to function like a perfectly synchronized orchestra. The planets don't speed up or slow down their internal clocks. They all dance to the same relentless beat. We can predict solar eclipses thousands of years in advance because the Moon and Earth are following their predetermined paths through absolute space and absolute time with flawless accuracy. We can send a space probe like Voyager on a grand tour of the outer planets using gravity assists to slingshot from one to the other because we can calculate their positions years, even decades in the future with utter confidence. This is the power and the glory of Newton's clockwork universe. This worldview bled into every aspect of science and culture. It gave rise to the Enlightenment, a period of immense optimism where thinkers believed that human reason, through the scientific method, could uncover all the secrets of nature. If the universe was a machine, then we could understand its workings. It influenced economics, with Adam Smith's invisible hand of the market seen as a kind of social physics. It even influenced ideas about God, who was often seen as the divine clockmaker who built the magnificent machine, wound it up with the laws of physics, and then let it run. But let's not forget the human experience within this vast machine. In Newton's absolute time, your life has a very specific structure. You are born at a fixed coordinate in space-time. You live your life as the projector's light moves through the frames of your personal timeline. You experience joy, sorrow, love, and loss in a sequence that is already laid out. Your memory is the record of the frames that have already been illuminated. Your anticipation is the expectation of the frames yet to come, and your death is the final frame in your sequence. But the great cold comfort of this universe is that your entire life, from first breath to last, always exists forever as a permanent part of the cosmic film reel. The past isn't gone, it's just a part of the reel that the light has moved away from. This was the comforting, orderly, and in some ways, terrifying picture of reality that Isaac Newton bequeathed to the world. It was a vision of a universe governed by law, not by caprice. A universe where things made sense. For over 200 years, this was the reality that scientists and everyday people lived in. It was a reality where time was a trusted friend, a steady guide, the one thing you could always count on. But as we know, even the most beautiful and solid-looking structures can have hidden cracks. And the first crack in Newton's magnificent cathedral appeared not with a planet or a cannonball, but with something much, much stranger, a beam of light. The constancy of light speed, that bizarre experimental result that refused to fit into the neat framework of absolute space and absolute time, was the tiny, insistent tap that would eventually bring the entire wall tumbling down, revealing a universe far more mysterious, far more dynamic, and far more wonderful than even Newton, in his boundless genius, could ever have dreamed. Then, in the early 20th century, a young patent clerk in Switzerland came along and shattered this comfortable picture into a million pieces. His name was Albert Einstein. Einstein's theory of relativity didn't just tweak Newton's ideas, it completely overthrew them. It told a story about the universe that was far stranger, far more beautiful, and far more mysterious. And at the heart of this new story was a radical rethinking of the nature of time. The first clue came with Einstein's special theory of relativity in 1905. He started with two simple-sounding principles. First, the laws of physics are the same for everyone, no matter how they're moving, as long as they're moving at a constant speed. Second, the speed of light in a vacuum is always the same for everyone, no matter how fast they, or the source of the light, are moving. This second principle seems innocent, but it's a bombshell. Let's unpack it. Imagine you're standing still and I throw a baseball to you at 60 miles per hour. You'll see it approaching you at 60 mph. Now imagine I'm on a train moving towards you at 50 mph, and I throw the same baseball at 60 mph in your direction. From your perspective, you'll see the baseball coming at you at 110 mph, the speed of the train plus the speed of the throw. That's common sense. Now replace the baseball with a beam of light. I'm on a super fast spaceship heading towards you at half the speed of light. I turn on a flashlight, shining it in your direction. Common sense would say you should see that light beam approaching you at 1.5 times the speed of light plus half the speed of light. But you don't. No matter what, you will always always measure that beam of light as traveling at exactly 186,182 miles per second. Not a fraction more, not a fraction less. It doesn't matter if I'm moving towards you, away from you, or sideways. The speed of light is the universe's ultimate speed limit, and it is absolutely constant. So we're left with this seemingly impossible situation. A beam of light from a moving spaceship approaches you at the same speed as a beam from a stationary flashlight. It defies all our intuition, all our experience with baseballs and trains and rain and sound. It's like a fundamental rule of the universe that simply refuses to play by the rules we grew up with. When faced with such a paradox, you have two choices. You can assume the experiment is wrong, that there's some hidden flaw, some measurement error we haven't caught, or you can do what Einstein did. You can take the result as gospel, as an unshakable fact of nature, and you can follow the logic wherever it leads, even if it leads you right off the edge of the map of common sense. Einstein chose the second path. He said, in effect, the speed of light is constant. This is our bedrock fact. If our current understanding of space and time makes this fact seem impossible, then it is our understanding of space and time that is wrong. This is a breathtaking leap of intellectual courage. It's like a detective realizing that the only way the crime could have happened is if the room itself was lying, if the walls could move, or if the clocks on the wall were untrustworthy. So he began to ask, what must be true about the universe for the speed of light to be constant for everyone? Let's really live inside this thought experiment for a moment. Imagine you're in a spaceship and you decide to measure the speed of light. In the center of your ship, you have a light source. On one wall, you have a mirror. You flash the light, it travels to the mirror, bounces back, and you time how long the round trip takes. Since you know the distance to the wall, you can calculate the speed. Let's say your ship is 186,282 miles long, so the round trip is 372,564 miles. You measure the time it takes, and it comes out to exactly 2 seconds. Perfect. The speed of light is 186,282 miles per second. Now, from my perspective, I'm watching you from another spaceship, and you are zooming past me at a huge speed, say 90% the speed of light. I decide to measure the speed of the same beam of light from my point of view. I see your ship go by. The light flashes in the center. But now, from my vantage point, your ship is moving. By the time the light beam reaches the wall at the front of your ship, that wall has moved forward from where it was when the light was emitted. So, from my perspective, the light beam has to travel more than half the length of your ship to catch up to that receding mirror. Then, on the return trip, the back wall is moving towards the beam, so it has to travel less than half the length of the ship. The path of the light, from my point of view, is not a straight line back and forth. It's a long forward slanting line to the mirror and a shorter backward slanting line back to the detector. It's a zigzag path. Here's the crucial part. According to Einstein's rule, I must measure the speed of that light beam as 186,282 miles per second. But I just watched it travel a longer total distance than you did inside your ship. How can it cover a longer distance in the same amount of time without going faster? The only possible answer is that it did not take the same amount of time. From my perspective, that light beam's journey took more than 2 seconds. Time inside your moving spaceship must have slowed down. Your seconds must have become longer, stretched out, so that from my outside view, your clocks are ticking more slowly. This is time dilation. It's not that your clocks are broken, it's that time itself is flowing at a different rate for you than it is for me. And it's not just time. To make all the math work out neatly, something has to happen to space as well. From my perspective, as you fly past me at near light speed, your spaceship isn't just experiencing slow motion time, it's also compressed in the direction of its motion. It gets shorter. If your ship was 100 meters long at rest, I might see it as only 50 meters long as it streaks by. This is called length contraction. The faster you go, the more you are squeezed in the direction you're traveling, from the point of view of a stationary observer. So let's state Einstein's breathtaking conclusion clearly. There is no fixed, absolute space. There is no fixed, absolute time. Instead, space and time are flexible, dynamic, and relative. They weave together to form a single, four-dimensional fabric called space-time. And your motion through this fabric determines how you experience the threads of space and the threads of time. The faster you move through space, the slower you move through time. It's as if every object has a fixed speed limit through space-time, the speed of light. If you aren't moving at all through space, you are pouring all your motion through the time dimension. But the moment you start moving through space, you have to borrow some of that motion from your movement through time. The more you use for moving through space, the less you have left for moving through time. At the speed of light, all your motion is through space, and your motion through time would come to a complete stop. For a photon, the particle of light, the entire journey from a distant star to your eye is instantaneous from its own perspective. It is born and absorbed in the same moment. It experiences no time at all. This is the heart of the twin paradox, and it's worth exploring in more detail because it highlights the strange logic of this new world. Astra, the traveling twin, boards her spaceship. She doesn't feel any different. Inside her ship, time feels perfectly normal. She eats, sleeps, reads a book, and everything seems fine. But from Terra's perspective on Earth, watching Astra's ship on a giant telescope, everything about Astra's life is in slow motion. Her heart beats once for every 2 of Terra's heartbeats. She turns a page in her book in what seems like a minute to Terra. Her journey to the star 10 light-years away might take, from Terra's perspective, 15 years. But because time is dilated for Astra, only say 7 years pass for her. When she turns around and comes back, another 15 years pass for Terra, but only another 7 for Astra. So, when the sisters are reunited, Terra has aged 30 years, but Astra has only aged 14. Astra is now 16 years younger than her twin sister. But wait, you might say, isn't all motion relative? From Astra's point of view, couldn't she say that she was stationary and it was Terra who zoomed away at near light speed and then came back? And if that's the case, shouldn't Terra be the younger one? This is the seeming paradox. The resolution lies in the fact that the situations are not symmetrical. Terra remains in a single, unchanging reference frame, the inertial frame of the Earth. Astra, however, does not. To turn around and come back, she has to fire her rockets. She has to accelerate and decelerate. She feels G-forces. She changes her state of motion. This breaks the symmetry. The one who feels the acceleration, who changes her path through space-time, is the one for whom less time passes. So, the paradox is resolved. Astra, the traveler, is unequivocally the one who comes back younger. And as we mentioned, this isn't just a thought experiment. We see it everywhere in particle physics. Muons are subatomic particles created when cosmic rays hit our upper atmosphere. They are unstable and decay into other particles in about 2.2 microseconds. Even traveling at 99.9% the speed of light, they should only be able to travel about 600 meters before decaying, far less than the distance to the Earth's surface. And yet, we detect them in abundance down here. Why? Because from our perspective on Earth, time for the high-speed muons is dramatically dilated. Their internal clocks are running so slowly that their 2.2 microsecond lifespan is stretched out, allowing them to complete the journey to the surface. From the muon's own perspective, it's not living longer. Instead, the distance to the Earth's surface is length contracted, so it has a much shorter path to travel. This brings us to the most profound and, for many, the most disturbing consequence of special relativity, the relativity of simultaneity. Newton's universe had a universal now, a cosmic present. Einstein shredded that concept. Let's explore the famous train thought experiment in more detail, as it truly shows how fractured our idea of now becomes. Imagine a very, very long train moving at close to the speed of light. You are standing on the embankment beside the tracks. At the exact instant that the precise middle of the train car is right next to you, 2 bolts of lightning strike the train. One hits the front end, one hits the back end. And crucially, these strikes are such that the light from both flashes reaches you, the observer on the embankment, at exactly the same time. Since you are equidistant from the 2 strikes, and the light reaches you simultaneously, you logically conclude, The two lightning bolts struck the front and back of the train at the same exact time. The events were simultaneous. Now, let's see this from the perspective of a passenger sitting in the exact middle of that same train car. She is also equidistant from the front and back of the car. What does she see? As the train is moving, she is traveling towards the light beam coming from the front of the train and away from the light beam coming from the back. Therefore, the light from the front strike will reach her first, because she is moving to meet it. The light from the rear strike will reach her later, because she is moving away from it. She sees one flash, then the other. What does she conclude? She concludes, with just as much logical right as you did, that the lightning bolt at the front of the train struck before the one at the back. They were not simultaneous for her. So, who is right? You on the embankment or her on the train? The stunning answer is, you are both right. There is no absolute God's eye view that can judge one of you wrong. Simultaneity is not absolute. It is relative. Whether two events happen at the same time depends entirely on your state of motion. Your now is not my now. There is no single, universal, present moment that encompasses the entire cosmos. This has a cascading, mind-shattering implication. It means that from the perspective of a spaceship moving rapidly towards you, what you consider to be the future might already be happening in there now, and what you remember as the past might still be the future for someone moving rapidly away from you. The concepts of past, present, and future lose their universal meaning. They become local, personal concepts, like here and there. We all inhabit our own unique personal slice of now that is tilted relative to everyone else's. The universe does not have a single timeline. It has a near infinity of personal timelines, all woven together into the four-dimensional fabric of space-time. This is why the GPS in your phone is a shrine to Einstein. The satellites are moving at about 14,000 kilometers per hour relative to the Earth's surface. According to special relativity, their onboard atomic clocks should fall behind clocks on the ground by about 7 microseconds per day because of this motion. But wait, there's more. General relativity, which we'll explore soon, tells us that because the satellites are farther from Earth's gravitational center, time actually runs faster for them by about 45 microseconds per day. The net effect is that the satellite's clocks gain about 38 microseconds per day compared to clocks on the ground. A microsecond is a millionth of a second. That seems tiny, but light travels 300 meters in a microsecond. An error of 38 microseconds per day would cause the GPS to accumulate a positioning error of over 10 kilometers per day. The system would be utterly useless. So the engineers must pre-program the satellite's clocks to tick at a slightly slower rate before they are launched, so that once in orbit, under the combined effects of both theories of relativity, they synchronize perfectly with clocks on the ground. Every time your phone tells you to turn left in 500 feet, you are performing a practical everyday experiment that confirms the flexible, relative nature of time. So, let's take a breath and absorb what Einstein's special relativity has done. It has dethroned time from its absolute monarchy. It is no longer the master conductor. It is a member of the orchestra, and its rhythm is influenced by its dance with space. We have moved from a universe of certainty and universal agreement to a universe of perspective and relationship. The solid ground of Newton's absolute stage has been replaced by the flexible dynamic fabric of space-time. And our journey is only half over. Because Einstein soon realized that this fabric isn't just a passive backdrop. It can be warped, curved, and stirred by the very things that live within it. This leads us to his even more radical general theory of relativity, and to the realization that gravity itself is not a force but a curvature in this space-time fabric. A curvature that bends not just the paths of objects, but the very flow of time itself. A decade later, he introduced his general theory of relativity, which wove gravity into this picture, and it did so in a way that further warped our understanding of time. General relativity tells us that what we perceive as gravity is actually the warping or curving of the fabric of space-time by mass and energy. Think of space-time as a taut, flexible rubber sheet. If you place a heavy bowling ball in the center, it creates a deep dimple. Now, If you roll a marble near the bowling ball, it will spiral in towards it, not because of some mysterious force pulling it, but because it's simply following the curved geometry of the sheet. Now, here's the crucial part for time. This warping of space also affects the flow of time. The stronger the gravity, the slower time passes. If you take a very precise clock and place it at sea level, and then take an identical clock and place it on top of a mountain, the clock on the mountain will run very slightly faster. This is because the gravitational pull is ever so slightly weaker at the higher altitude, further from Earth's center. The sea level clock is in a slightly deeper gravity well, so its time is stretched out, running slower. This effect, called gravitational time dilation, has also been measured experimentally with incredibly accurate atomic clocks. So, we have two ways that time can be stretched and slowed: by moving very fast, special relativity, and by being in a strong gravitational field, general relativity. This means that time is not a background stage, it's an active player in the cosmic drama. It's part of a four-dimensional fabric called space-time, and this fabric can be bent, stretched, and warped. So we've seen how Einstein turned the universe into a four-dimensional tapestry where space and time are interwoven, and where moving quickly through one affects your passage through the other. But for Einstein, this was only half the story. Special relativity was a brilliant description of the universe, but it had a limitation. It only worked for observers moving at constant speeds. It described a universe without acceleration, and most importantly, without gravity. And gravity, as Newton had so powerfully shown, was everywhere. This nagged at Einstein. He knew his theory was incomplete. The breakthrough, the happiest thought of my life, as he called it, came from a seemingly simple image. He imagined a man falling from a roof. In that moment of free fall, the man would feel weightless. If he dropped an object, it would float beside him as if gravity had vanished. This led Einstein to a radical idea. What if the effects of gravity and the effects of acceleration are, in a deep, fundamental way, indistinguishable? This is the equivalence principle. Let's play with this. Imagine you're in a windowless, perfectly sealed elevator. If this elevator is sitting perfectly still on the ground, you feel your normal weight. Your feet are pressed against the floor. If you drop a pen, it accelerates downwards. Now imagine this elevator is suddenly pulled upwards with a perfect constant acceleration of 9.8 meters per second squared, the same as Earth's gravity. Inside, what would you feel? You'd feel pressed against the floor, exactly as if you were standing on Earth. If you dropped a pen, the floor of the elevator would accelerate upwards to meet it, making it look exactly as if the pen were falling towards the floor. There would be no experiment you could do inside that box to tell whether you were sitting still in a gravitational field or being accelerated through empty space. This was Einstein's brilliant insight. Gravity isn't some mysterious invisible force reaching out across space and pulling on things. Instead, it's a feature of the landscape itself. The presence of mass and energy doesn't create a force. It warps the very fabric of space-time around it. And objects moving through this warped landscape simply follow the most natural path available to them. They follow the curves. This is where the famous rubber sheet analogy comes in, and it's worth exploring in a bit more detail while remembering its limitations. Imagine space-time as a vast, taut, flexible rubber sheet. This is our stage. Now, place a heavy bowling ball in the center. It creates a deep dimple, a depression in the sheet. This massive object, like the sun, has warped the space-time around it. Now take a marble and roll it past the bowling ball. It won't travel in a straight line. It will curve inward, tracing a path around the dimple. It might even go into orbit. From a bird's eye view, it looks like the bowling ball is attracting the marble, but there's no attraction. The marble is simply following the contours of the curved surface. It is taking the straightest possible path through a curved geometry. This is what gravity is. The Earth isn't being pulled by the sun by some invisible string. It's simply following its natural inertial path, a geodesic, through the space-time valley that the sun's mass has created. Now, let's bring this back to time, because this is where it gets truly mind-bending. If mass and energy warp space-time, and time is part of that fabric, then gravity must warp time too. The curvature isn't just spatial, it's temporal. Think back to our rubber sheet. The dimple represents a gravity well. The steeper the sides of the well, the stronger the gravity. Now imagine that the flow of time is like a pattern of tiny perfect grid lines printed on that rubber sheet. When the sheet is flat, far from any mass, the grid lines are evenly spaced. Time flows at its standard rate. But when you create a dimple with a heavy mass, those grid lines get stretched and distorted. They are closer together in the depths of the dimple. This stretching of the grid lines is a metaphor for gravitational time dilation. The stronger the gravity, the deeper you are in the well, the more the time part of the fabric is stretched. This means that clocks tick more slowly where gravity is stronger. It's not that the mechanisms of the clock are broken, it's that the very thing the clock is measuring, the passage of time itself, is flowing at a slower rate. This isn't just a cool idea. It's a measurable, everyday reality for physicists. We mentioned the clocks on GPS satellites. Special relativity says their speed makes their clocks run slow. But general relativity says that because they are farther from Earth's center of mass, in a weaker gravitational field, their clocks should run faster. The two effects don't cancel out. The gravitational effect is stronger. So, overall, the satellite's clocks gain about 38 millionths of a second each day compared to clocks on the ground. If we didn't deliberately build this correction into the system, your navigation would fail completely within hours. Every time you use your phone to find a coffee shop, you are relying on the proven fact that time runs faster 12,000 miles above your head than it does right here in your hand. We can measure this on Earth too with astonishing precision. Scientists have used atomic clocks so accurate they wouldn't gain or lose a second in billions of years. They synchronized two of these incredible clocks. One they kept at sea level, the other they placed on a table just a foot higher. After a day, they compared them. The clock on the table, experiencing ever so slightly weaker gravity, was running infinitesimally faster. It had ticked a few extra times. Your head is technically aging faster than your feet. The difference is fantastically small, but it is real. The universe is literally telling us that time passes at different rates for different parts of our own bodies. Now, let's take this to its extreme because that's where the real fun begins. What happens when gravity becomes unimaginably strong? We find the ultimate laboratory for general relativity at the end of a star's life, a black hole. A black hole is what you get when a colossal amount of mass is crushed into an infinitely tiny point, a singularity. This creates a gravity well so deep that not even light can escape it. The boundary of no return is called the event horizon. Imagine a brave astronaut, let's call her Celeste, on a mission to study a black hole. She is in a spacecraft a safe distance away, and she is monitoring a probe that is being lowered towards the event horizon. From her safe vantage point, she watches the probe on her screens. As the probe gets closer and closer to the event horizon, it falls deeper into the black hole's gravitational well. From Celeste's perspective, a truly weird thing happens. The probe appears to slow down. Its signals, which are pulses of light, start to arrive further and further apart. The light itself is getting stretched out, its wavelength lengthening, shifting towards the red end of the spectrum, a phenomenon called gravitational redshift. This is because time on the probe is slowing down relative to her time. As the probe approaches the very edge of the event horizon, from Celeste's point of view, it seems to freeze. It never quite crosses the line. The signals become infinitely delayed, the light becomes infinitely red, and the probe appears to hover, frozen in time for all eternity. Meanwhile, from the probe's own perspective, time is passing perfectly normally. It would cross the event horizon without any fanfare at a specific moment on its clock, and continue its journey into the unknown depths of the black hole. There are two completely valid but utterly different descriptions of the same event. For the outside universe, the probe's time has effectively stopped. For the probe, the universe's future is rushing by in a blink. This is the ultimate expression of time's flexibility. Gravity doesn't just bend the path of light, it bends the flow of time itself to the point where it can appear to bring it to a standstill. So, let's put all the pieces together. We now have two powerful engines that can manipulate time, Velocity and gravity. Special relativity says the faster you move through space, the slower you move through time. General relativity says the deeper you sit in a gravitational well, the slower you move through time. Your personal experience of time is a unique blend of these two effects. Every single object in the universe, from a whizzing electron to a sleeping cat to a spinning galaxy, has its own personal clock, its own rate of time, determined by its precise motion and its precise location in the gravitational landscape. This finally completes the demolition of Newton's stage. Time is not a background actor. It is not the conductor. It is an integral part of the orchestra, a player whose rhythm is determined by a complex dance with its three spatial partners and the mass energy content of the universe. Space-time is a dynamic, elastic entity. It can ripple. We have detected these ripples, called gravitational waves, from the collisions of black holes billions of light years away. The fabric of the cosmos itself can stretch and vibrate like a drumhead. It can expand, carrying galaxies away from each other as the very grid of space between them grows. This brings us to perhaps the most profound and strangely beautiful conclusion of all. If time is so relative, so personal, so dependent on one's path through the cosmos, then what does it mean for the universe as a whole? Many physicists interpret the equations of relativity to be describing a block universe, a static, four-dimensional structure where all of time, past, present, and future, exists simultaneously. In this view, the Big Bang, you reading this sentence, and the distant heat death of the universe are all just fixed locations in a vast, frozen, four-dimensional landscape. The feeling of time flowing, of the now moving, is a cognitive illusion, a necessary artifact of how our conscious brains, themselves physical systems within this block, sequentially process information. We are like a reader who can only see one word of a book at a time, believing the story is being created as we read, when in reality, the entire novel is already written, from the first page to the last. We are not moving through time. We are extended in time, much as we are extended in space. The you of 5 years ago, the you of this moment, and the you of 5 years from now are all equally real, just at different temporal coordinates. This is a deeply unsettling idea for most of us. It seems to rob us of free will. It makes the future seem preordained. It challenges our very sense of being agents who can change things. But it is a direct, and many physicists argue, inescapable consequence of Einstein's theories. If the laws of physics are symmetric and don't pick out a special now, then the block universe is the most straightforward interpretation. However, the story doesn't end there. While relativity gives us a grand, large-scale picture of space-time, there is another pillar of modern physics that deals with the impossibly small, quantum mechanics. And when we enter the quantum realm, things get even weirder, and the nature of time becomes even more mysterious. Quantum mechanics is the physics of atoms and subatomic particles. It's a theory of breathtaking accuracy and predictive power, but it operates by rules that defy all common sense. In the quantum world, particles don't have definite properties until they are measured. They exist in a fuzzy cloud of possibilities, a superposition of all possible states. An electron is not in one place or another. It is in all possible places at once, with a certain probability of being found in each location when you look. It's only when you make a measurement that this cloud of possibilities collapses into a single definite reality. This already plays havoc with our classical notions of objects having a well-defined history. But what does it say about time? Strangely, the core equation of quantum mechanics, the Schrödinger equation, treats time in a very Newtonian way. It assumes a smooth, background universal time. It doesn't incorporate the time-warping effects of general relativity. This is one of the biggest problems in all of physics: how to reconcile the curved space-time of general relativity with the fuzzy probabilities of quantum mechanics. We need a theory of quantum gravity, and we don't have a complete one yet. Some approaches to quantum gravity, however, offer fascinating new perspectives on time. One of the most prominent is the concept of entropy and the arrow of time, introduced by the physicist Arthur Eddington. He argued that relentless statistical increase in entropy is what gives us the arrow of time. It is the physical process that tells us which way is past and which way is future. We remember the past because it was a state of lower entropy. We can't remember the future because it is a state of higher entropy. Think about a movie. If you were shown a single random frame from a film, you could probably make a very good guess about what came before and what comes after, not because you've seen the movie, but because of entropy. Take a frame showing a shattered wine glass on the floor. You know with absolute certainty that the previous frames showed a whole glass falling off a table. You know the future frames will show the pieces still on the floor, or perhaps being swept up. You would never ever see a film run backwards where pieces on the floor assemble into a glass that then leaps up onto the table. Your brain instinctively understands that such a sequence violates the arrow of time. The past is the state of the whole glass, low entropy. The future is the state of the broken glass, high entropy. Now, let's scale this up. Way up, to the biggest isolated system we know, the entire universe. The second law of thermodynamics applies to the universe as a whole. This means that the total entropy of the cosmos is always increasing, and this is the engine behind our experience of time's flow. The reason we feel time moving forward is that we are living in the aftermath of a cosmic event of unbelievably low entropy. What was that event? The Big Bang. Physicists believe that the universe began in an incredibly hot, dense, and, this is the crucial part, extraordinarily ordered state. The early universe was a nearly perfectly smooth soup of fundamental particles and energy. This might not sound ordered, but in thermodynamic terms it was. Imagine a balloon filled with two different colors of sand, perfectly separated, red on one side, blue on the other. That's ordered low entropy. Now shake the balloon. The sands mix into a uniform purple. That's disordered, high entropy. The Big Bang was like that balloon at the moment of the first tiny shake. It was a state of pristine, unfathomably low entropy. Ever since that moment, the universe has been expanding and cooling, and its entropy has been relentlessly increasing. Galaxies form, stars ignite, burn their fuel and die, scattering heavy elements across space. Planets form from the debris. On at least one of those planets, the flow of energy from a hot star to a cold space drives complex processes that lead to life. Life itself is a local phenomenon that creates beautiful pockets of order, a cell, a tree, a human brain, but it does so by consuming energy and increasing the total entropy of its surroundings. We are like little eddies in a great river, temporary structures of order that form as the water rushes towards a state of maximum disorder. This is the grand narrative of time. The flow we feel is the universe progressing from its highly ordered beginning towards its ultimate state of maximum entropy, often called the heat death. In this far, far future, the universe will be a vast, cold, and incredibly dilute soup of particles, all at the same temperature. There will be no more energy gradients, no more hot spots and cold spots to drive any process. Everything will be in a state of thermodynamic equilibrium, maximum entropy. The cosmic clock will, in a sense, wind down because there will be no more processes left to give time its arrow. So, where does this leave us? We have two powerful but seemingly conflicting pictures. From relativity, we have the block universe, a timeless, static, four-dimensional landscape. From thermodynamics, we have a universe with a clear, irreversible arrow of time, flying from a low-entropy beginning to a high-entropy end. How do we reconcile them? Many physicists see the block universe as the underlying reality. The entire timeline from the Big Bang to the heat death is just there. But within that block, the property of entropy provides a direction. It labels one end past and the other end future. Our conscious experience, our sense of a flowing now, is then a phenomenon that emerges from this cosmic gradient. We are like fish who can only swim one way in a river. The river itself, the block universe, exists all at once, but the current, the increase of entropy, gives us an undeniable direction of travel. We are carried along by the rising tide of disorder, and that journey is what we perceive as the passage of time. It's a humbling and magnificent thought. The reason you can remember your childhood but not your old age, the reason you can make an omelet from eggs but can't turn an omelet back into eggs, The reason we feel that time is slipping through our fingers, all of it traces back to a single momentous fact about the origin of our cosmos. We are all, every one of us, living testimony to the universe's one-way trip from order to chaos. And in that journey, in this constant struggle against the tide, we find the meaning of our moments, the poignancy of our memories, and the precious, fleeting beauty of now. But does this mean time is real? Or is the flow still an illusion, with entropy just providing a direction on the static block of space-time? Some physicists, like Carlo Rovelli, a leading thinker in loop quantum gravity, argue that at the most fundamental level, time might not exist at all. In his view, the equations that will ultimately describe quantum gravity might be timeless. They would describe the relationships between events, not their evolution in time. Time, in this picture, would be an emergent property, a macroscopic approximation that arises from the way these quantum events are correlated with each other, much like the concept of temperature emerges from the average motion of molecules, even though a single molecule doesn't have a temperature. So, where does this leave us? We've journeyed from the flexible clock of our own minds, through the absolute time of Newton, into the relative and warped time of Einstein, and down into the timeless, probabilistic world of quantum mechanics. We've seen time as a static block and as an emergent arrow born from cosmic disorder. Is time an illusion? The answer, it seems, is both yes and no. The way we experience it as a universal, flowing river is almost certainly an illusion. There is no single now, no master clock, and the future may be as fixed as the past in the grand geometry of space-time. Our perception of its flow is a clever trick of our consciousness, a way for our brains to make sense of the world. But is it all an illusion? Probably not. Something is happening. The universe is changing. Entropy is increasing. We remember the past and not the future. There is a clear directionality to causation. So, while the flow might be a psychological artifact, the asymmetry of time, the difference between past and future, seems to be a real feature of our cosmos, rooted in its initial conditions. Perhaps the most helpful way to think about it is to see time as a story with two layers. There is the underlying reality, which might be a timeless block of space-time, a network of quantum events, a vast, frozen landscape. And then there is the story we live, the narrative we create as conscious beings moving through this landscape, illuminated by the spotlight of our attention, experiencing the world one moment at a time, feeling the weight of memory and the pull of anticipation. That feeling is real. The joy of a moment that flies by, the agony of a moment that crawls, the nostalgia for the past, the hope for the future. These are the very substance of our human experience. Time may be an illusion, but it is a magnificent and necessary one. It is the stage upon which the drama of our lives unfolds. It gives our choices meaning, our loves poignancy, and our stories a beginning, a middle, and an end. So, the next time you feel time speeding up or slowing down, remember the incredible complexity behind that simple feeling. You are not just a passive passenger on a river of time. You are a timekeeper in your own right, a storyteller navigating a cosmos of breathtaking mystery, using the most powerful and perhaps the most beautiful illusion in the universe to live, to learn, and to love. Good night. Have a deep, calm sleep.